Thank you for coming. My name is Vladan Djakovic. I'm Director of IoT Infrastructure at iDevices. And in this talk, I'm going to do a quick overview and present you our IoT infrastructure. This is something we developed in the company. It's been running for years now, pretty stable. So this is the real thing. The agenda is mostly technical. In the first part, I'm going to do introduction to Coyote, why we did it, what are important things about that. And in part two, I'm going to go through two examples of applications that are using our infrastructure for their daily operation. In short, the infrastructure is extremely low cost because it's built with IoT in mind. This is a true edge-to-edge infrastructure. We built it for our own devices initially, and now we are selling essentially access to third parties using the same thing. The cost starts for sensor devices that sends a couple dozen packets per day at less than $1 per device lifetime. This is an important thing. Infrastructure is not sexy, but you need to have it. And you usually cannot afford to pay several dollars per device a year because over the lifetime that accumulates and essentially beats all the cost models that you have. There's no onboarding. Everything regarding authorizing access happens during manufacturing. So there are no actions required after manufacturing to authorize access to the infrastructure. It's all already done. And it's very fast. Again, it is edge-to-edge. We pushed everything we could from the backend to the edge and retained the basic services that you cannot do without at the backend itself. So we have cut the costs of related to connecting devices down to the fraction of the BOM, bill of materials. That's the main reason why you should look at this thing. There are no extra interactions from the regarding infrastructure required from users or from developers for that sense. So you can focus on your apps, you can focus on your firmware, and you don't really need to worry about the infrastructure itself. The security and anonymity was built into the architecture of this infrastructure. The first item are self-assigned address space. We don't care how you call yourself. We don't give you names. You give identifiers and names to yourself. Infrastructure doesn't really know who is accessing it and has no way of knowing. And there is also end-to-end encryption layer in addition to client-to-server encryption, which operates on SDK. So we encourage customers to use that, in which case we don't even know which data you're exchanging. The speed is essentially limited by the speed of light because the switching time is typically under 1 millisecond. So your end-to-end latency is equal to internet speed, the speed of the packets themselves. The SDK is available for multiple platforms. It's very has very low footprint, 130 kilobytes of code and 10 kilobytes of RAM on ARM architectures with a full crypto stack. What something is common to all the services that we supply. First of all, it's all UDP based. We work with IPv4, IPv6, and you can mix and match. IPv4 client can talk with IPv6 client. Clients can be embedded devices, handset, or third-party backend servers. All high availability resilience is delegated to clients, so it's very fast. Servers are basically stateless. So in case of outage, the clients quickly figure out how to find alternate path, and I will show later on how that works. And again, stressing that the credentials, the access credentials, which we call coins, are embedded preferably during manufacturing. There are two basic services that we provide, and there's a third service, which I will talk a bit later on, which enables interface to third-party applications. The two basic services are real-time conduit and time-shifted e-storage. E stands for ephemeral. It's a short-term storage. So conduit is for real-time communications. Servers are essentially reflectors. Transactions are processed extremely fast. The way it works is that clients agree on on identifier. We call it CCID. They agree in advance. you can think of it as a pin. If it's very long, it's possible to guess. You agreed it when you provision them, or you pair client with the handset, or you pair client with the backend server. It's up to the application. There is a session model. So essentially, you open the connection with the credential. You keep it alive by pinging the server, and then you close the timeout. The opening overhead is usually 1 packet per minute, very low. I will show those packets later on. Compare this to TCP connections, which is far more chatty and has far more load on the bandwidth and on your routers. There are 2 client roles. Accessory, which is usually an embedded device, which has to open the connection first, like the server. You can think of it as a server. And there's a controller, which is usually handset, but could be another embedded device or backend server, which can then connect to this particular connection. As I mentioned, scaling high availability is handled on the client side. It's calculated that we don't use DNS. We are not vulnerable to any DNS attacks. And the way it works, once the clients are talking happily over one particular connection, because we have multiple servers deployed out there, and when they detect a problem, they are going to calculate an alternate server and connect to that. So basically, these interruptions are not perceived by clients in most cases. I will go back to when I go about switched and explain a bit more how this works and why is this essentially never experienced by the customer. E-storage is time-shifted communication. It's a distributed key value store. Records up to a bit more than 1 kilobyte. The key has 2-level structure, so the base is 94 bits. I'm sorry, yes, 94 bits, and 104 bits, I'm sorry. And so you can store about 16 gigabytes per the base key. You can think of that as a file space, but it's used for many different things. We use it for logs. We use it for analytics. We use it for live video streaming. Because for live video streaming, this is broadcast model, you have a bunch of readers on the same stream. Operations are write with confirmation, overwrite, which is protected by public cryptography, and there is a read. There are no deletes, records simply silently expire. Writes are atomic, which you can use for a bunch of different situations. There is a session concept in a sense that you obtain an authorization token, which is valid for a week, and it's sent with each packet to access. The important thing to understand is that this is UDP-based. So for example, to write a record, most of the time it's 1 packet out. A single packet out causes a record to be written. I'm not actually aware of anything that is more lean than this. There are 2 types of storage. One is short-term, it's 4 hours, and the other is medium-term, 7 days. And the medium-term storage has redundancy of 2, so it's backed up. When is this storage used? Well, essentially whenever you don't need the receiver to be immediately available. The typical use cases are sensor reports, logs, video streaming, and video recording. Firmware updates. You can put firmware out there, and device is going to pick it up and update by its own pace. And also you can do, as I mentioned, locks, because the writes are atomic, which is very useful when you try to coordinate hundreds of devices to do something. The third type of service are application gateways. They enable your fabric to connect with pretty much anything. These gateways run on your servers if you have a specific application. They are redundant, and you decide what redundancy factor you want. You decide how much you want to scale them, how many you want to put there, depending on the load. It's all provided by design. And on each server, we provide you a code. You get a source to connect to our fabric, and then you put any application you like there. The two communicate through Unix domain sockets. The clients send packets using e-storage type of access. So they essentially send the packet, but the payload will be delivered to the application gateway, to your server. Delivery to the server is guaranteed, so you don't lose packets there. Use cases, keeping state. Whenever you have to keep state outside from handset and client, that's what you can use this for. We are using that to send push notifications and SMSs for alarms. You can use it for analytics. So basically, this is your opening gate to legacy applications and new applications that you need that are more complex than this what this edge-to-edge infrastructure provides. We took a great care to provision for security. There are two separate layers. And I will mention that our security is audited, and the audit report is available to our partners. We take this very seriously. So a lot of time was spent making sure that we can plug all holes that we know of and make sure that the ones we don't know of are unlikely. The first layer is client-server security. It's unconditional. We use elliptic cryptography and AAD cipher to send and receive packets. There is forward secrecy involved, in the sense their session keys are never transported with long-lived secrets, with long-lived keys. Clients change keys every 8 hours, servers change keys every day. Full payload is protected, including the address part, so nobody can guess which channel you're using to communicate. And there is a separate layer of security. This is a different cipher suite. Here we use RSA and Blowfish. It's implemented in SDK. It also has forward secrecy and supports all authentication modes. Why is this important? If one layer fails, say somebody breaks RSA or somebody breaks the elliptic curve, there is a second layer left there to protect your data and your clients from data breach. And again, an inherent part of security is that servers don't keep any data. We cannot even afford to keep any data if we want to switch in 1 millisecond. So all we see are IP numbers where data comes from. We see CCIDs and CSIDs, but we don't know who is talking to whom. They can switch these things many times if they want. So we essentially retain nothing. So breaking into the infrastructure is not going to reveal anything. There is no gain by hacking into our infrastructure. This is what pushing everything to the edge brings. SDK protects against replay attacks, although we use UDP. We have very efficient protection against replay attacks. And again, because identifiers are protected with encryption, there is no way to do client-specific denial of service. Authorization, as I mentioned, is enabled through use of coins, which are bearer certificates. Typical thing is we sell 10,000 or 50,000 coins to a manufacturer. They put them in devices during manufacturing, and that's it. Those devices will be able to access our infrastructure. Of course, the price of the coin depends on the usage pattern. It's not the same if you send 10 packets a day or you use high-definition video streaming. But the point is, this is the only contact where you need to basically pay for the connectivity. From then on, it's essentially painless. Coins are different. They define different service levels, different kinds of usage. The infrastructure has no way to relate coins to individual devices it uses because you put them in devices. We don't know where you put which one. So we don't have that information. It is also possible if you don't want to put coins during manufacturing, you can give them or sell them to users. So you can enable any subscription model without having to have special accounting service or something like that. So that's also possible. What do we have? We have infrastructure which we have deployed. It's been running now for about 2 years. It has 100% uptime because of the resiliency model we mentioned. Of course, servers have been dying. Bandwidth providers have been dying. We have dual bandwidth providers for each node. So when one dies, the other one is still there. Actually, we had a problem last night for about 2 hours. One of our providers at one of co-locations failed, but clients do not feel that. It's monitored, it's tested, it's been upgraded several times. We have upgrade pipes for live during operation. So that's what we are offering here as a service. There are also licensing options where you can choose to run infrastructure on your own machines. Developers see SDK. We have extensive SDK which have been ported. There's a C, basically core in C, and there is abstraction layer ported to several platforms. We also will be providing Python interface to that, Python wrappers to the SDK. From SDK, the infrastructure looks like session infrastructure. You get full source for crypto libraries, and some things that are notably implemented in the infrastructure other than regular session opening maintenance is this end-to-end encryption, reliable transfers, e-storage public crypto for overrides, And there is a crosscast. Crosscast is a library which enables you to quickly provision Wi-Fi device without anybody entering access point mode. And you can provision many devices at the same time, and it takes about 2 seconds for this. And I'll come back to that. There is also the debugging framework, iTranscript, where essentially gives you logical traces of your packets between devices, so you can debug your application. So now we're coming to part 2, which are the use cases of this infrastructure, and I will introduce 2 separate use cases. One is a switch device, and the other one is sensor device. They use different parts of infrastructure. One uses conduit, and the other is using storage. But before I get there, I just want to ask, are there any questions regarding the first part?
Which kind of infrastructure do you use?
I'm sorry?
Which kind of infrastructure do you use? Cell phones, Wi-Fi?
So most of devices right now use Wi-Fi, but the SDK needs basic IP stack. We're using UDP, right? So whatever is there, we can use it. The rationale to use this on cellular devices is very simple, because we're going to use less bits to move information than any other infrastructure. So essentially, your cellular costs are going to be lower if you use this to move the same kind of data, because there is no maintenance of the session, of TCP/IP sessions. They're not continuous heartbeats, whatever. You know, it's really low on usage.
So you use UDP mostly, right?
We use only UDP. Yes. Okay, thank you. Anybody else? Okay. Switch. Switch is actually exhibited at our booth there. It's remote control of line power. So essentially, you turn it on, and it connects to our infrastructure, and you can control it now with application and handset. I will focus only on parts which are using our infrastructure. There are many parts of this application, and we can talk to them later on if you have interest in that. So what happens first? During manufacturing, a switch gets its coin, and it authorizes a particular usage pattern that is expected from the switch. And then when it's out of the box, it's being provisioned and paired. To end user, it's essentially one operation. But logically, provisioning enables switch to access local Wi-Fi access point. And pairing is exchanging credentials with the handset, so that particular handset will have authorization to access this particular switch later on. Once that's done, I'm just showing some of traffic here. One thing that every device does, including switch, is it's refreshing the service listings once a day. This is not related to resiliency, high availability. This is basically handling the addition to infrastructure, which happen very rarely, but still, we check it once a day. And here you can see this dump of these packets to basically get to the whole listing of current infrastructure. The total exchange is a bit less than a kilobyte. So it's very low log. So when you power on the switch, it associates with access point, opens a conduit connection on the CCID that it agreed on with the handset when they were paired, and waits for handsets. It sends a packet to backend every minute to keep the connection open. This is important because this is how we keep the net open, because all of the switches, pretty much all of them, are behind some kind of net. And this is what keeps net open and enables packets from infrastructure to reach the switch. When a controller connects, a switch gets a packet from the infrastructure telling it that controller has connected. So it's aware, even before controller says anything. This is a comparison of packet traces with TCP dump and iTranscript. As you can see, iTranscript has half the lines because it's logical, it combines multiple lines into logical messages. When the user turns on the handset, there's going to be some exchange between handset and switch. There are 2 modes of packet exchange. One is data through mode, where you send direct UDP packet, very low overhead. Keep in mind that in normal traffic, about 1,000 packets is lost. The other mode is reliable mode, where this has higher overhead. The packet size is larger, 64 kilobytes, and if there are losses, they will be retransmitted. So there is more overhead, it's slower, more packets, but it's reliable. Which one are you going to use really depends on the semantics of your message. If missed message is very important, then you want to use reliable mode. And if late delivery is not good, you want to use UDP. For example, if you are direct datagram mode. For example, if you want to turn the light on and you're there and you press the button and there are network problems, light doesn't come on, what user is going to do is push the button again. Your packet eventually arrives. So there are two packets coming there, one to turn it on, one to turn it off, and that's totally unexpected behavior. So sometimes it's better to have a lost packet than to force the reliable mode. You can also tunnel protocols over this, and we are actually tunneling Apple's HomeKit protocol over this because our devices are HomeKit compatible. So we push HomeKit over our infrastructure. This is, again, an example of a dump. You can see what it looks like to send a packet between handset and the device. From the handset point of view, the only difference is that it cannot open connection until the accessory is already there. So the open fails if the accessory is not present. Otherwise, it's pretty much the same. Also, the handset doesn't need to have a coin. It's using proof of work, so handset do not need to be provisioned. Basically, you only pay for the device, and everybody else gets a free ride. Backend servers can also be controllers, not just handsets. So if you want to emulate some other protocol, you can emulate thousands of handsets on the backend server and have a different protocol behind that one. We also have that, actually. We use that. As you can see, the basic interactions in a switch are client-server model. Switch waits, client comes in and talks to it. The communication is effected through key-value pairs, and nothing special about that. And as I mentioned, the security is based on CCID, which is hidden from the rest of the world by encryption. And there is also end-to-end security because these two clients agreed on public key pairs when they were paired. So there are two layers of security here as well. Sensor is actually, let me ask you, are there any questions here about this device before I move to the sensor? Okay. Yeah, go ahead. I'm sorry? How?
How is it configured provisioning?
Oh, provisioning. In the case of the switch, provisioning is done as a part of HomeKit provisioning because we were using that as a provisioning model. Now we also adding Android support. So provisioning is basically application-dependent thing. We do not force it with infrastructure. We have a way of provisioning, which I'm going to explain on sensor device, but we're not using that for a switch for historical reasons. But during provision, essentially, the two exchange keys, and they authenticate each other before they do that. In the case of HomeKit, there is a chip in the device, so that it has its own unique thing, and you can recognize its signature. In case of Android, we use different method, but it's always you authenticate two sides, and then once they understand they're talking to who they want to talk, they exchange keys.
So, I mean, the push mode, it will work if the data speed is low. How about streaming data?
We have application there, actually, it's installed. We have video streaming.
Okay.
So video streaming, we use actually storage.
So a different approach, right? It's not a push, it wouldn't work.
For video streaming, for video streaming, we use e-storage. So again, the camera device, the streamer, is sending stream of UDP packets to e-storage. That's how it works. And they get stored there. We use one CCID, and we have a file structure there. We use TS segments there, right? So one segment is full. The next one gets there. And the readers simply find what is now, and they go and read it, right? So for streaming, the device is pushing to e-storage because e-storage is always there.
Yeah, but I mean, but it's a different kind of, very minimum difference between this one and the previous one, right? But
Well,
talking about other like big data, streaming, fast data, they'll be different.
no, but the video data is compressed. So on this device we use H.264 compression. So the video is compressed. So there are iframes and p-frames. So that's all taken care of far before our infrastructure comes into play. It's already done. So the video, we do not move raw video. Nobody can do that.
So your API, like a RESTful API as well as streaming API?
No, we don't offer any REST API. We don't do any TCP/IP. It's too slow.
You focus on endpoint. You don't do any API gateway.
In case of streaming, it's the source device, camera device, and the infrastructure, and it's one way, right? Because infrastructure is always there.
Okay, so that's like an uplink, only uplink.
Yes, because camera doesn't need to download anything, and the viewers, they send a request per packet and get packet back, request per packet, get packet back.
That's very typical use case. There are a lot of different kind of use cases, bidirectional, both uplink and downlink.
Yes, that's what conduit is for. That's what conduit is for. That's what conduit is for. The one I just talked about, it's two-way communication, and then two sides told it's P2P. They can send and receive packets, and they have two modes, this datagram mode and reliable mode, but it is two-way communication, yes. So certain device is very low bandwidth. What it does, it sends periodic heartbeats that it is okay, and then when is a reason for alert, it sends out alert. Typically what it is detecting is temperature range, vibration, presence of water, and things like that. The way it works is that it has ultra short duty cycle, which means that it sleeps most of the time. It wakes up every couple hours, connects to the access point, sends one packet that is okay, and goes back to sleep. Typical cycle is less than 500 milliseconds. This means that you have very long battery life while using Wi-Fi. And e-storage enables this because e-storage doesn't require anybody else to be there when this guy wakes up, so it's always there. This is why you can do this with our infrastructure. User gets notification when there are actual alert or when the device fails to report, and I'm going to go through details how this happens. It's using application gateway and e-storage, actually application gateway through e-storage, because there is really no need for real-time communication with end user unless there is an alert, and application gateway takes care of that. So to go quickly through the moves of the provisioning. During provisioning, we use Crosscast to provision this. So it's a one-way communication, and it provisions one or more devices at the same time. It's affected by your handset, any handset or computer, and nobody here gets to the access point mode. So it takes usually less than 2 seconds to send a couple of kilobytes of data to the device, and usually what you will send it is how to access a Wi-Fi access point, how to contact the user, which identifiers to use, the name and location stored, and so on. The point being is that all data for this application is stored on the device. This is the only time that you tell who to contact and where it is and what to do. The data lives on the device. It doesn't live on the infrastructure. These are traces of the crosscast provisioning. Because this is a one-way thing, there is e-storage component. When the device receives crosscast packet and can access the access point, then it sends one particular e-storage packet so that handset knows that it has been provisioned. So that's the back channel. E-storage is used as a back channel. And here are a couple of lines of code which device affects during provisioning. This is what handset does. It basically sends crosscast packets, and then it waits and polls backend to see if the specific e-storage packet has come back, in which case it knows it can stop because device has been provisioned. Again, this is going to work on multiple devices at the same time. This is very convenient if you want to provision 100 devices at the same time. You don't have to do each one individually. In normal operation, like it said, the device wakes up, connects associated access point, and does one e-storage application gateway write. Each payload has environmental data, temperature, whatever, device ID, and then it goes back to sleep. Actually, these are lines of code which happen during this wake period. It's very short, less than half a second. This is why we can use full power Wi-Fi radio and still have years worth of battery life. When an alert happens, like water leak has been detected, it wakes up immediately. It also sends a storage application gateway right, this time with confirmation, because it will not go back to sleep until it knows that infrastructure has actually received the payload. And then it's done. Its duty is done. The package has been delivered. The rest is done by application gateway. This is typical storage open, write, and read. Again, illustration here is really of IO transcripting, which gives you logical lines instead of TCP dump raw traces. What does application gateway do? Well, when it receives heartbeat from a device, if it was already there, it updates the timestamp. If not, it knows there's a new device there, so it makes a new record for that. The records are made in memory. Application gateways are replicated, so this happens typically in more than one. Nothing goes to disk, and there is no need to back this up. Once device checks in, it's expected to keep checking in at the stated interval. If it doesn't, the user will be informed. The information to inform user is contained in every packet from the device. So this is very, very lean, very, very, very thin thing. And you don't need to worry to back up or maintain your backend servers because they don't hold any critical information. You can bring it down, bring a new one up, and just going to collect all the devices as they report. There is a separate process, of course, for decommission devices because you don't want alerts if you want to turn them off. And when there is a need for alerts, in this particular case, we use separate services to send push alerts. We use Twilio for SMS and Apple Push for Apple devices. And you can make it as complicated as you like, that you may require user interaction to confirm receiving alert before you stop sending and so on. So that was essentially the talk. The intent was to give you kind of overview how different this is, how thin this is, that everything has been pushed to the edge. So, and this is why we can offer the costs which are essentially impossible to reach by anybody else. Sure, go ahead.
I assume that switch does not need to save power too much, right?
Switch does not need to save power. Yes, switch is on all the time. Why does not the switch?
Yeah, because switch sends data down or up to the servers, right?
Mm-hmm.
Yeah. Why you don't put error recovery or whatever inside the switch?
Well, a switch is using reliable mode when it needs to use reliable mode. A switch is using the reliable mode and implementing SDK. So although the basic infrastructure is UDP, we have SDK provided reliable mode of transfer, which means when you give a message to it, it will be delivered sooner or later. And if there are losses, the packets will be replicated. They will be resent. So that exists in the SDK, at the SDK level. So for switch, for important things on switch are using the reliable transfer mode, yes.
Do you know, are there any way, do you know, are there any way at the endpoint side that you can help the whole system to scale better? You know, in cloud, data center side, of course, I mean, the platform.
Yeah, but this infrastructure scales linearly.
Linearly?
Yes, totally linearly.
Why?
I'm sorry?
Why? Suppose 1 million cell phone users are uploading the photo or video, right? To the data center or cloud. If the data center or cloud side, they cannot handle scalability issue very well.
Well, it's okay. So the two different types of scaling. There is this peak loads, which I think you are referring to, right? We do not handle dynamic scaling for peak loads. If you don't understand, we are going after industrial use, about millions of devices. So if you look at our load curves, they're flat. We don't see peaks because there are so many of them. So what we are doing, we can scale up, not in real time, but you know, we can add infrastructure as our demand as our user base grows up, and that is linear because there are no single choke points in there. There's no, yeah, sorry.
To control the cloud side, you told me you can scale up in infrastructure-wise. So,
yes.
Which means you also take care of the cloud data center?
Yeah, we run our own servers in our own cabinets in our collocations on bare metal. And we buy bandwidth directly from multiple tier one bandwidth providers. And we buy space from premium collocation providers. We are in Equinix, for example. So to scale up, for example, if you want to go to 20 million devices from 5 million support now, it's a couple of weeks. Yeah, essentially, we put bulk.
It's not inconvenient.
No, it's not. No. But when you're dealing with high number of devices, you don't see instantaneous things.
So you have to do capacity planning and then add more machine, or buy more powerful.
Yes. But the infrastructure again does scale linearly because all load sharing, load balancing, and failover is handled by clients. We push that to the clients. We push the load balancing to the client side.
That's pretty good. So when you mentioned scale up, did you mean it sort of make your cluster larger, or just keep the size of a cluster fixed same, but you replace with more powerful machines?
Oh no, we add nodes. Our machines are fixed size.
Add nodes.
Yeah, add nodes. We add nodes. So our machines are fixed size.
So the bare metal are commodity machines.
Yes, exactly. So we have a standard pizza box, right? A server. It's and just we add more. And it's totally. I mean, you can add on live infrastructure, and they're going to be commissioned within 24 hours, and they're just going to become a part of the. Yes, but it's a cost, when you run your own and buy bandwidth wholesale, it's one cost model.
It's under your own control.
Yeah, so I mean, all infrastructure is really reselling electricity, and there is, in this case, there are less middlemen. Okay. Thank you very much.